Good evening, everyone. Welcome to NPTEL tutorial session for the course Classics in Total Synthesis taken by Professor Krishna P. Kaliappan from Department of Chemistry, IIT Bombay. My name is Sri Lakshmi. I am a fourth year PhD scholar in the Department of Chemistry in IIT Bombay. So, this is our seventh tutorial session, and so far we have discussed several uh, topics related to topics and reactions to the contents which were discussed in the various tutorial sessions, and we have discussed several problems as well. So so in the last class we stopped by discussing this week 4 assignment, and so today firstly we will see a discussion on the week next week lecture starting from gibberellic acid. This was the first lecture of week 6 lecture contents, and that was about gibberellic acid, and this was a continuation of the week 5 lectures. So, in Corey's total synthesis of gibberellic acid, we have seen the intramolecular Diels-Alder reaction, iodolactonization, epoxylactonization, radical cyclization, Claisen rearrangement were the major steps, and they utilize cyclopentadiene as the starting material. And we have also seen what is iodolactonization, what is its mechanism, and how the key intermediate is prepared via four pathways, and then what is Diels-Alder reaction, what is hetero Diels-Alder reaction. So we have seen up to the intermediate in the 24th lecture. And in the 25th lecture, we have seen the application of iodolactonization, Novanagal condensation, and Friedel-Crafts cyclization in the total synthesis of gibberellic acid by Yamadas group. So, in as we said, the Corey's total synthesis was completed in 1982, where the key reactions were 4 plus 2 cycloaddition and iodolactonization, and they could complete the total synthesis in 31 steps with 0.5 percentage overall yield. And coming to Yamada's total synthesis, which was completed in 1989, the starting material used was methyl pyruvate, malononitrile, and the key reactions included Novanagel condensation, lactonization, 4 plus 2 cycloaddition, ozonolysis, and Corey-Chekhovsky reaction. And they completed this total synthesis by utilizing 42 steps with 0.3 percentage of overall yield. Now, in the next lecture, we have seen the total synthesis of perhydrohistrionicotoxin, where we have seen the application of pinacol-pinacolone rearrangement and Barton reaction in the total synthesis of histrionicotoxin. And this molecule is isolated from the venom of Columbian frog, Dendrobatus histrionic. That's why it got this name. And the core structure, as we can see here, it involves a spirofused ring, a six-membered ring fused with a piperidine ring with two side chains. And the key reactions include pinacol-pinacolone rearrangement, Barton reaction, Beckmann rearrangement, and the starting material used is cyclopentanone. Now, E.J. Corey completed this total synthesis in very few steps. So that was one remarkable total synthesis of this perhydrohistrionicottoxin. Now, coming to strychnine, so the lecture 27, 28, and 29 was about strychnine. So we had a very long discussion on this strychnine. So in the first lecture, lecture 27, we have seen that Woodward's total synthesis from isostrychnine and Woodward's relay approach. So this coming to this molecule, this strychnine, it was isolated in 1918 from Strychnos vomica, and so this is actually a poisonous molecule. We can say the composition of 50 mg and above of this strychnine is fatal. So structurally it is having the seven rings, and the correct structure was proposed by Woodward in 1948 using UV. It was this proposed structure was finally confirmed by X-ray, and it is having seven fused rings, six stereo centers, and out of which five are contiguous and in one ring, and it has a unique seven membered ring, unique spirocenter. So these were the major synthetic challenges associated with the synthesis of this molecule. So the degradation products of strychnine will give isostrychnine, Whelan Gemlich aldehyde. So in Woodward's total synthesis, the key steps utilized was Fischer-Indol synthesis, Manich reaction, Baer-Villiger oxidation, and we have seen a Woodward's relay approach where the intermediate was obtained by degradation as well as through isostrychnine. Now, in the lecture 28, we have seen the total synthesis of strychnine by Ravel and Overmann's group, where we have seen the application of Diels-Alder reaction and Heck reaction in Ravel's total synthesis, and Asakov-Manich reaction in Overmann's total synthesis. So, Ravel's total synthesis was also through isostrychnine, and it was completed in 1994, where the key reactions were intramolecular Diels-Alder reaction and intramolecular Heck reaction. And in the Overman synthesis, which was the first asymmetric total synthesis of minus strychnine, the key reaction involved Asakov-Manich reaction to assemble the pentacyclic strychnine core, where they completed the total synthesis in 20 steps with 3% of overall yield. And they used this Whelan Gumlich aldehyde as the starting material, and they have also used Chile coupling as one of the reaction. And the starting material used by the Overmann's group was cyclopentadiene. Now, in lecture 29, we have seen the total synthesis of strychnine by QN. So, there we have seen a racemic as well as an asymmetric total synthesis of strychnine by QN from isostrychnine and Whelan Gumlich aldehyde, respectively. And they have utilized tandem Manich Cope rearrangement and Manich reaction, tandem condensation, sigmatropic rearrangement, and cyclization sequence to complete the total synthesis. So the racemic total synthesis was completed in 14 steps through isostrychnine, and asymmetric total synthesis was completed through 14 steps from Whelan Gumlich aldehyde from tryptophan, which they got in 5.3% of overall yield. So before going through some of the reactions which I have discussed in this lecture contents, you can quickly go through this lecture contents, and then we will go into detailed mechanism of some of the reactions mentioned here. Okay, now moving ahead. So now we will see the mechanism of some of the reactions which I have told during discussing while discussing the lecture contents. So the first one is novenagel condensation. So here what is happening? A ketone and a compound having a ketone and a compound having this activated methylene group in the presence of an amine base dehydration kind of reaction is happening, and we are getting this alpha beta unsaturated compound. So what is the mechanism? So firstly, from this activated methylene compound, this deprotonation is taking place by the this piperidine will take this proton and it will form this intermediate which can exist in this enolate form as well. So once it is in this form, it can attack on this carbonyl carbon center and can form this intermediate. Then this O minus can take the proton from this piperidine and it will be this OH. So again, then what can happen is this base can take other proton from this active methylene group, and this bond will come over here and this will come over here, and it will form this kind of active alpha beta unsaturated carbonyl compound. So this reaction is known as Novanangel condensation. So this proton abstraction from this active methylene compound, then it will attack over this center. This will become OH. Then second proton abstraction of this active methylene compound, and then dehydration will result in this alkene, and it will be an alpha beta unsaturated compound. And this reaction is known as Novanangel condensation. So these are some of the examples for this Novanangel condensation. So this is benzaldehyde, acetyl acetone. We will be getting this 3-benzylidene, 2,4-pentane dione, and benzaldehyde malonic acid. We will be getting cinnamic acid. Salicylaldehyde diethyl malonide. We will be getting ethyl coumarin 3 carboxylate. So these are some of the examples for Novanangel condensation. Now the next reaction is Korey-Chaykovsky reaction. Then we have pinacol-pinacolone rearrangement, Barton reaction, Beckmann rearrangement, Fischer-Indol synthesis, Manich reaction, Baeyer-Williger oxidation, Heck reaction, and Stille coupling. Then we will go on with the week 5 assignment discussion. So this Korey-Chaykovsky reaction, it is the reaction of sulfur halides. So sulfur halides will react with carbonyl compounds in the presence of DMSO to form this epoxides or aciridin. So if it is reacting with carbonyl compounds, we will be getting epoxide, and if it is reacting with amides or imines, we will be getting aciridins as the major product. And the reaction of sulfur halides with enones will give the cyclopropane also. So that is known as Korey-Chaykovsky cyclopropanation. So the mechanism is, first the halides are generated in situ by deprotonation of sulfonium halides with strong bases. So the sulfonium halides in presence of base will form the halides. Then base can take proton from one of this methyl group and it will form this halide type of compound. So then what is happening? This dimethyl oxosulfonium methylide, known as Korey-Chaykovsky reagent, is valuable alternative to dimethyl sulfonium methylide and can be generated from trimethyl sulfoxonium iodide. So if we use this trimethyl sulfur, we will be getting this particular halide, and if we are using this trimethyl sulfoxonium, we will be getting this particular halide. Then what is happening? That negative charge formed by the proton abstraction from one of the methyl group will attack at the 1,4 position of this alpha beta unsaturated compound, and this will go here and this will come here. Then when the O minus will come back, O minus will come back, this double bond will go and attack this carbon, forming this intermediate, and this DMSO will be eliminated. So this is the mechanism of Korey-Chaykovsky reagent. You may quickly go through it, then we will go to the next reaction. So what is happening? This halide formation, then that halide will attack over this alpha beta unsaturated carbonyl compound, and when this will come back, this will go and attack over this CH2, and this will be eliminated as DMSO. That is known as Korey-Chaykovsky reaction. So if it is with carbonyl compound, it will be formation of epoxide. If it is with acid amines, it will be forming aciridins, and if it is with alpha beta unsaturated carbonyl compounds, it will be forming cyclopropanes. So now moving ahead with the next reaction, that is pinacol pinacolon rearrangement. So here what is happening is that this pinacol, so which is basically a diol, it will react with the sulfuric acid. So one of this hydroxyl group will get protonated, and then it will be leaving to form this carbocation. Then one of the methyl group from the adjacent position will migrate to this carbocation, so that it will form more stable carbocationic intermediate. Then proton transfer will take place to get the pinacolon. So this is pinacol, and this is known as pinacolon. I think we have also already discussed this pinacol pinacolon rearrangement in previous session. Okay, so now moving ahead with the next reaction, that is Barton reaction. So Barton reaction, what is happening? This kind of this also we have discussed previously. So I just quickly go through it. So this kind of nitroso compound. So radically this will cleave and O radical and this NO radical will form. Then this proton transfer, hydrogen transfer will take place from this position to this position, generating a radical at this center, which will combine with this NO radical to form this intermediate, which can be written exist in this form as well. So this is known as Barton reaction. Now, the next reaction is Beckmann rearrangement. So, it is a rearrangement of ketoxime into amide. So, what is happening? This ketoxime in the presence of acid is getting rearranged to form this amide. So, how it is happening? First is this, in this alcohol of this ketoxime is getting protonated. This OH2 is leaving. This nitrogen lone pair will take this R1 is migrating, and this bond will shift to here to form this intermediate, which can exist in this form as well. Then this water molecule will attack over this carbon and it will form this intermediate, and a loss of proton will give this compound. Then again this nitrogen will get protonated, and this oxygen lone pairs will come over here, and that will come neutralize this positive charge on nitrogen. Then again proton loss will form this amide. So this is the mechanism of Beckmann rearrangement. Now the next reaction is Fischer-Indol synthesis. So here what is happening, this aryl hydrazone is rearranging to form this indol kind of derivatives by utilizing this proton transfer and acid catalyzed elimination of ammonia. So firstly what is happening, this nitrogen will get protonated, and then this elimination of one proton from this center will give this intermediate. Then again this nitrogen will again get protonated, and this bond will come over here, this will shift over here, and this will come over here to form this intermediate. So this can exist in this form as well, this double bond NH. If it is aromatized, it will be NH2 with double bond here. Then this nitrogen lone pair will attack over this carbon center of this imine to form this intermediate. Then elimination of one NH3 and one H plus will give this indole derivative. So this is known as Fischer-Indol synthesis. And here we have given some examples for this Fischer-Indol synthesis. So when phenylhydrazine is reacting with acetophenone, we will get this 2-phenylindole. And when this phenylhydrazine is reacted with this cyclohexanone, we will get this 1, 2, 3, 4 tetrahydrocarbazole. So the next reaction is managed reaction. So here if we are treating this formaldehyde or an enolizable ketone or secondary amine with these three together with an acid, we will be getting the product as ketone, product with ketone as well as amine functionality. So what is the mechanism? First of all, this formaldehyde will get protonated to form this compound, and to that this nitrogen lone pair will attack over this carbon to form this intermediate. Then proton loose from this nitrogen center will give this compound. Then what is happening, this nitrogen lone pairs will fall over here and this bottom molecule will eliminate to form this iminium ion. Now this iminium ion, yeah, before that, this ketone which is having alpha hydrogen, it will eliminate one alpha hydrogen to form this intermediate, and then the iminium ion will attack over this carbon will attack over this carbon of this iminium ion to form this compound, which can lose this proton to form this beta amino ketone. So this is known as managed reaction. So formaldehyde, an enolizable ketone, and secondary amine will be reacting to form a product which is having a ketone and amine functionality. Now the next reaction is Bayer vinegar oxidation. So here this ketone and a peroxy acid like MCPBA or H2O2 will react and form this ester intermediate. And if we are using a cycloketone with this peroxy acid, it will form this lactone compound. So here what is the mechanism? Here, this ketone will get protonated with this peroxy acid to form this protonated ketone and this percarboxylate. Then, this oxygen lone pairs will attack over this carbon and this will shift over here to stabilize the positive charge on oxygen to form this intermediate. Then, this oxygen lone pair will come here and this will this will come over here and this will leave as this carboxylate and this protonated ester. Then again this carboxylate will take this proton of this positively charged oxygen and it will form this ester as well as this carboxylic acid. So the carboxylic acid of the corresponding peroxy acid will be the byproduct and we will be getting this ester as the major product. Now, the next reaction is Heck reaction. So, in Heck reaction, we have already seen this mechanism as well in the previous lectures. So, here an alkyl halide and alkene is reacting in the presence of a palladium catalyst and a base to form this coupled compound, an alkene. So, what is the mechanism? First, this oxidative addition will take place over this palladium catalyst of this alkyl halide to form this intermediate. Then this alkene insertion will take place, which can form either this intermediate or this intermediate. Then this beta hydride elimination, and this reductive elimination will give the catalyst back, and this will be the compound. This coupled alkene will be the compound. And the next reaction is Chile coupling. So this is the coupling between aryl halide and this organocyanines in the presence of palladium catalyst to form this coupled product. So here also first step is oxidative addition. Then CO. So this mechanism is for like carboxylative Stille coupling. So here CO insertion is an additional step. Then this transmetallation is taking place and reductive elimination will give the product. So this type of reaction is known as Stille coupling. With tin, the coupling is happening. Now moving on to the week 5 assignment question. So the first question is identify the major product in the following transformation. So this compound upon treatment with this lithium perchlorate and calcium carbonate in THF, which will be the major product here. So four options are given. Try to find out the mechanism of the reaction as well. So here the correct answer is option A. And what is happening here? This tosyl chloride pyridine condition, as we will get the starting material. So this will be selectively tosylated, and then this oxygen lone pair will come over here. This oxygen lone pair, this OH will eliminate, and no, this oxygen lone pair will come over this center, and this bond is migrating to this position, and this OTS is leaving under this condition to form this compound. So, firstly, this tosylation, then this oxygen lone pair will fall over here. This will migrate over this center, and OTS will leave. Now, the next question: what is the major product formed in the following transformation? So, this compound, upon treatment with this SOCl2 and pyridine, which will be the major product? So here the correct answer is this option B. So what is happening? This is getting eliminated actually in this condition to form this double bond. Now the next question, identify the type of cycloaddition reaction taking place in the following transformation. So this compound, upon this exposure to this mercury lamp, we are getting this compound. We are getting this compound. So here, which will be the type of cycloaddition? 3 plus 3, 3 plus 2, 2 plus 2, or 4 plus 4? Which cycloaddition reaction is taking place here? So here the correct answer is 2 plus 2. So this is a 2 plus 2 photocycloaddition reaction, which will give this product from this starting material. Now the next question is, what is the major product formed in the reaction given below? So here this compound, upon treatment with this compound having active methylene group in the presence of ethanol, which will be the major product formed here. So here the correct answer is this option A, and this mechanism we have already discussed. So this proton abstraction will take place from here and it will attack over this center, and then elimination will take place, dehydration will take place to form this compound A. Now the next question, identify the major product formed in the following reaction. So this compound, upon treatment with this SnCl4 in DCM, which will be the major product here. So here what is happening is that, so this is the, so here the correct answer is this one, option C. And what is happening? This is a kind of cyclization reaction. So this SnCl4 can coordinate with this oxygen. Then this will attack over the Cl minus will attack over this center. This will attack over here. This double bond will come over here, and this OH will leave. So it will give this compound C as the major product. Now moving to the, sorry for that. Moving to the next question, identify the reagents causing the following transformation. So this compound is converted into this particular compound. So out of this reagent combination, which can give this transformation? So here the correct combination of reagents is option B. So what is happening first in the presence of the zinc, silver and this diiodomethane, this cyclopropanation will happen to this double bond. So this is Simon-Smith reaction. Then this PTO2H2 will PTO2H2 condition, this will be converted, this bond will be cleaved and this hydrogenation will take place to form this dimethyl compound. So the correct answer is option B. Moving to the next question, identify the major product formed in the reaction below. So this compound upon heating, which will be the product formed here. So here this is the 4 plus 2 cycloaddition reaction, and we will be getting this option A as the major product with this ester and this hydrogen in the cis stereochemistry, and both these protons will be in trans stereochemistry. Moving to the next question, identify the major product in the following transformation. So this phenolic derivative upon treatment with this allyl bromide and K2CO3 in first step, and then heating it up to 220 degrees Celsius, and then ozonolysis, which will be the major product. So here what is happening first, this O-allylation is taking place in the presence of this allyl bromide to give this compound. Then Claisen rearrangement is taking place when it is heated up to 220 degrees Celsius, that is 3,3 sigma tropic rearrangement. So this group will come over here. Then ozonolysis will give the corresponding aldehyde. So the ozonolysis will, yeah, so then this will shift over here and ozonolysis will happen. At that time this oxygen can attack over this center, and it will form 1 2 3 4 5, and here OH will be formed. So ozonolysis and then cyclization is also happening. So if we, so this cannot form because 3,3 sigma tropic rearrangement will give this ortho substituted product, and then this ozonolysis and further cyclization can happen, and it can give this kind of intermediate. Now the next question, identify the major product of the following reaction. So this compound upon treatment with the sodium bicarbonate and iodine Ki at 0 degrees Celsius, which will be the major product. So here the correct answer is, firstly what is happening, this cyclization will happen, this oxygen lone pair will attack over this center to form this compound, and this will be quenched with this iodine. So firstly what can happen, iodonium ion can form, and then O minus will attack over this carbon, iodonium ion will open to form this compound. So the correct answer is option D. Moving to the next question, identify the major product in the below reaction. So this compound upon heating, which will be the major product formed here. So here what is happening? This TMSO triflate will form the enol TMS over this center. Then a 3,3 oxycop rearrangement will take place to form this compound, which can be rewritten as this one. That is option C is the correct answer. So with this we will conclude today's session. So if you have any doubts, let me know. And we will meet in next Saturday for the next tutorial session. Thank you for listening and thank you for joining. Thank you.